Now I'm going to define trigonometric functions, and I'm going to start with the two basic ones, sine and cosine. Recall that a unit circle is a circle of radius 1. If we take a horizontal and vertical axis and draw a unit circle centered at the origin, then if I take a ray from the origin to the edge of the circle, that makes an angle x with a positive horizontal axis, then the point at which it cuts the circle has coordinates cosine x, sine x. So that gives me a definition of cosine and sine. And because this point is on the circle, we immediately have a formula. Cosine squared x plus sine squared x has to be equal to 1. The hypotenuse of this triangle has length 1. The horizontal side has length cosine x, and the vertical side has length sine x. So that triangle corresponds to this triangle in the picture on the right. Now what this picture on the right is about is if I take any right-angled triangle with any hypotenuse of length h, the other sides are a and b, and let's suppose this angle at this corner is x. I can slide this triangle into this corner and it fits perfectly because the angle is x. What I get is that because that angle is the same and they're both right-angled triangles, then the third angle must be the same, so these are similar triangles. And that means that the ratios of the sides must be equal. A over h must be cosine over 1. That's because a divided by h here must be equal to the ratio of the corresponding sides in the smaller triangle. But remember, we know that the length of that red side in the smaller triangle is cosine, and the length of the hypotenuse in the smaller triangle is 1. Likewise, the ratio b over h in the large triangle must be equal to the ratio of the yellow side over the hypotenuse in the smaller triangle. But we know that that's sine of x over 1. We don't have to rely entirely on the unit circle. If someone gives me a right-angled triangle with a hypotenuse of any length and an angle x in the corner, then sine of x is the opposite over the hypotenuse, and cosine of x is the adjacent over the hypotenuse. Now, there are various techniques for remembering that. I believe there's something called SOHCAHTOA, which also includes the tangent function. Sine is the opposite over the hypotenuse, SOH. Cosine the adjacent over the hypotenuse, CAH. And tangent is the opposite over the adjacent. We'll see what that means in a second. Well, the definition of the tangent function is the opposite, the b over a for this triangle, but it's also equal to sine of x over cosine of x. If you do the calculation, that turns out to be b over h over a over h, and the h's cancel, so you get b over a for any given right triangle with x in the appropriate corner there. So this is something that people often use to remember sine, cosine, and tangent, and how they line up in this right-angled triangle. Notice that these angles are all between 0 and 2 pi radians. We're always going to talk about radians in this course, especially when we do derivatives. It's really important to remember that angles are measured in radians. A circle, 360 degrees, is equated to 2 pi radians. So we've defined this for x values between 0 and 2 pi. And then we extend that definition to all real numbers by saying that whatever x is, sine of x plus 2 pi is always the same as sine of x. For any number x, you can always keep chopping bits of 2 pi from it to find something way back here in the interval from 0 to 2 pi with the same sine value. So for this one, if I subtract 6 pi from it, I get something between 0 and 2 pi, and the sine of x equals sine of x1 here. And the same with cosine. We define cosine of x equal to cosine of x plus 2 pi, and then we can always compare it to something in the interval from 0 to 2 pi. So these functions repeat on every interval from 0 to 2 pi. So this extends our definition to all of the real numbers. Now notice that the cosine and the sine are always between -1 and 1. The highest value of the sine is 1 here, and the lowest value is -1, and the highest value of cosine is 1, and the lowest value is -1. And then there are various other trig functions. I've told you already that tangent is sine over cosine, cotangent is cosine over sine, secant is 1 over cosine, and cosecant is 1 over sine. And they're also defined for all real numbers except when the denominator is equal to 0. There are several values of sine and cosine that it would be very wise to memorize because we're going to use them quite a lot in this course. And it's good to be able to tell almost immediately what sine and cosine of 0, pi over 6, pi over 4, pi over 3, and pi over 2 are. 0 is not terribly difficult. If you look at the ray from the origin that makes the angle 0 with the horizontal axis, then basically it cuts the circle where the horizontal axis cuts the circle. And it's pretty easy to write down the coordinates of that point. They're just 1, 0. So that gives you that cosine of the angle here, 0, is 1, and sine of the angle is 0. It's good to memorize either pi over 6 or pi over 3. Pi over 6 corresponds to 30 degrees, but we always measure in radians. If you draw the ray that comes from the origin making the angle pi over 6 with the horizontal axis, then it cuts the unit circle at the point √3 over 2, 1 over 2. So that gives you cosine of pi over 6 is √3 over 2, and sine of pi over 6 is 1/2. Now one can derive that using right triangles, but it's good to memorize either pi over 6 or pi over 3. Pi over 4, if you use it often enough, you're going to remember this one. You're going to remember all of them if you use them quite often. But if you forget the sine and cosine of pi over 4, it's pretty easy to reconstruct them. This ray that comes from the origin making an angle of pi over 4 with the positive x-axis lies along the line which is the diagonal of the plane, and the coordinates of every point on that line are always equal. So you know that cosine pi over 4 equals sine pi over 4. And furthermore, you know that this point lies on the unit circle, so the sum of the squares is 1. Now, notice here, just in case of any confusion, we write the squares of these trig functions in this way. Well, if the two are equal, this is saying that 2 times cosine squared pi over 4 is 1. That tells you cosine squared pi over 4 is 1/2. And hence cosine pi over 4 must be 1 over the square root of 2, and because sine is equal to it, it too must be 1 over the square root of 2. And of course, the square root of 2 over 2 is 1 over the square root of 2. Now for pi over 3, it is 60 degrees, and the ray that creates an angle of pi over 3 with the positive x-axis is a reflection of the ray corresponding to pi over 6 through this diagonal of the plane. And when you reflect a point through this diagonal, the perpendicular reflection, you switch the two coordinates. So if you remember one of these, you get the other. If you remember sine and cosine for pi over 6, then you get the sine and cosine for pi over 3 by switching the coordinates. And for pi over 2, well, you could use that switching trick for 0, but it's pretty easy to see where the ray coming from the origin making a right angle with the horizontal axis cuts the unit circle because it runs along the vertical axis. So the coordinates here are 0 and 1, and that gives you cosine of pi over 2. Cosine 90 degrees is 0, and sine is 1. Now it's also important to be able to use the unit circle and its symmetry to find sine and cosine of other angles. So for example, let's suppose I want to find sine of 5 pi over 6. Well, let's have a look at where this sits on the unit circle. The straight angle is pi, and so 5 pi over 6 is this angle here, and the ray defining it makes an angle of pi over 6 with the left-hand side of the horizontal axis. So we'd like to find the second coordinate of this point. Now here's where the symmetry of the unit circle helps us. If we reflect this ray in the vertical axis, we get another ray which makes an angle pi over 6 with the positive part of the horizontal axis. So the coordinates of this point over here are cosine pi over 6 and sine pi over 6. But I know those. I know that this is root 3 over 2, and this is 1 over 2. Now what happens to the coordinates when I reflect them in the vertical axis? The second one remains the same, so the 1/2 is still positive, but the root 3 over 2 goes to negative root 3 over 2. So now I see not just sine of 5 pi over 6, that's the same as sine of pi over 6, but I can also write down cosine of 5 pi over 6 is minus root 3 over 2. Let's try to do this for a negative angle. Let's find cosine of negative pi over 4. Well, what I mean by negative pi over 4 is the angle I would get if I were to drag that positive part of the horizontal axis in a clockwise direction for pi over 4 radians. So this is the angle minus pi over 4. And again, I use the symmetry of this unit circle. Suppose I were to reflect this angle in the horizontal axis, or reflect the ray that defines the angle in the horizontal axis, then I get an angle of pi over 4 here. And I know that the coordinates at this point are 1 over root 2, 1 over root 2. Now what happens when I reflect this point back through the horizontal axis to get the original point? Well, the first coordinate remains the same, and the second coordinate now becomes negative. So we have cosine of minus pi over 4 is 1 over the square root of 2, and sine of minus pi over 4 equals minus 1 over the square root of 2. Notice also that this ray defining cosine minus pi over 4 is the same ray that defines cosine 7 pi over 4. So those two angles differ by an angle of 2 pi, so the cosines are the same. In other words, 7 pi over 4 is equal to minus pi over 4 plus 2 pi. So the sine and cosine of 7 pi over 4 is the same as the sine and cosine of minus pi over 4. Now, because sine and cosine are the coordinates of a point on the unit circle, we observed before that sine squared plus cosine squared of any angle must be equal to 1. And also we saw there's some symmetry in the unit circle, so that gives us that sine of the negative of an angle is minus the sine of the angle, and cosine of the negative of an angle is cosine of the angle. In particular, sine here is an odd function, and cosine is an even function. So as you might expect, there's going to be some symmetry in the graphs of these functions. This gives you the graph of sine of x. You can see it oscillates between minus 1 and 1. On the interval from 0 to 2 pi, it completes a full wave. That wave is repeated on every subsequent interval of length 2 pi. Likewise, cosine has symmetry in the vertical axis, and cosine completes a wave from crest to crest for x in the interval from 0 to 2 pi, and then that wave is repeated on every other interval of length 2 pi, starting at some multiple of 2 pi. And we can figure out one more very useful identity here. By dividing this first identity by cosine squared, we get that tan squared plus 1 is secant squared of x. So these are 4 identities that you should keep in mind when you're working with these functions.